we said we can't place complex numbers on the number line. And that's true. But we still want a way to visually represent the numbers and where they sort of sit. And we do that using what's called an Argand diagram, named after a French, I think he's a Frenchman. Guess what his surname was?
Argand.
Oh, okay, good. You've heard about him. All right.
Get more research.
Now, the Argand diagram actually looks very familiar. It looks like a number plane. And it's sort of what it is. But what it is not so much the number plane. X is actually the real number line, where we place the real numbers. And Y, if you like, is the imaginary number line. This becomes a real axis, and Y becomes an imaginary axis. And that then gives us a unique position for every single number. For instance, if I want to plot the number 2, well, it's still just like normal. I'll put it on the number line at 2. There it is. But if I wanted minus 3i, something that's purely imaginary, then I place it on the imaginary number line down at minus 3. And something that's a mixture, well, it's just like coordinates. The x coordinate becomes the real part, the y coordinate becomes the imaginary part. And so we have minus 2, 1, there it is. So minus 2 plus I. If I want to put 4 minus I, there we go, we plot 4 minus I. But look at this one, 4 plus I. Hey, that brings up an interesting feature. Conjugates then must always be a reflection in the real axis. Because remember we said the only difference was the sign of the imaginary part. So the real part's going to be the same. The imaginary part's going to change sign. So there'll be reflections in the real axis. Now, how about if I took a negative of a number? So the negative of 4 minus I, so the negative of D if you like, which would become minus 4 plus I. So it would be over there. Now look at that in relation to D, and it's also a reflection, but this time through the origin. So a negative of a number is reflected through the origin. Another way of thinking about that is rotation. You think, oh, well, I've rotated the point, again, through the origin, but I've rotated it 180 degrees. How about if I multiply a number by I? So if I multiply D by I get 1 plus 4i, which is placed up there. And that's where this idea of rotation comes in handy. It's a bit hard to describe a reflection of D to get G, but if we talk about a rotation, that's a lot easier, because actually that's been rotated 90 degrees. And so every multiplication by I, think about it, is a rotation of 90 degrees. Remember over here, F, we said was multiplied by negative 1, multiplied by I, multiplied by I again, so you've multiplied by I squared, which is negative 1, so you've rotated 2 lots of 90, 180 degrees. So every single complex number has a unique position on our Argand diagram. So I can now describe lines in the Argand diagram similar to the way we did it on the number plane. Right? So a horizontal or vertical line, well, in Cartesian geometry, we would have said, oh, that's the line y equals c. But now when we talk about complex numbers, I say, oh, well, that's the line that represents the imaginary part of z is equal to c. So that's all the numbers whose imaginary part is c. And a vertical line, well, that would be all the real numbers that represents, in this case, k. So all the real numbers that have all the numbers that have a real part, I should say, of k. Circles, in Cartesian geometry we saw as x squared plus y squared is the radius squared. X squared plus y squared, real part squared plus the imaginary part squared was z times z conjugate. So I could write that as z times z conjugate is equal to r squared. So I'm going to find and describe. Well, this will turn out to be a circle. You notice the z times z conjugate, but the other numbers you'll notice are conjugates as well. And just to prove it, let's expand the whole thing out. Whee, tidy it up. Lots of z's in there. Let's substitute in x and y so we can see what the Cartesian equation is. And a bit of completing the square to be done, but we eventually get it. So it actually is the circle x plus 4 squared, y plus 1 squared is equal to 49. Now, have a look at the original one. Yes, there was z times z conjugate, but remember, circles we usually say minus the centre, and that is in fact what we've done, because you see you've got 4 plus I minus the centre. There it is, 4 plus I. And then the other one is the conjugate. So when you've shifted the centre, instead of having z times z conjugate, you have z minus the centre times z minus the conjugate of the centre. And the radius, of course, in this case is 7. So if you see z minus conjugate, conjugate z minus conjugate of the other number, you know you've got a circle. 1 plus z plus 1 over conjugate of z is equal to 1. Have no idea when I first look at that what that's going to be. So just like when we were dealing with locus in coordinate geometry, if we have no idea, well, let's go back to coordinate geometry. Let's sub x and y's in and then let's see what happens. So, well, before I do that, I'm going to tidy it up. So I now have conjugate plus z is equal to z times z conjugate. Z times z conjugate, there it is again. So x squared plus y squared. Z plus the conjugate, twice the real part. So I've got 2x. Looks like I've got another circle here. X squared minus 2x squared plus y squared is equal to 0. Tidies up to be x minus 1 squared plus y squared is equal to 1. I've just got to be careful though, because that was not the original question. Like it's a circle, centre 1 naught, radius 1 0. Have a look at the original question. Would there be any exclusions on this one? So what was that one? Z can't equal... Does 0 lie on that circle, I guess is what we're saying. So in this case, we'd have to exclude that point, because the original question, it wouldn't satisfy. And also the conjugate, because we're talking about 0, well, conjugate of 0 is 0. All right, we shall play with 1C.